Do I share the screen or not yet?
Yeah.
Yet.
Okay.
No.
This is for Christian's 60th birthday, a very special occasion. And now today our the second speaker is Matilde Martinez, and her title is Unique Ergodicity of the Horizontal Flow for Remaining Foliations. Okay,
Well,
you can.
thank you very much. I'm very happy to be here. I chose to speak about this subject because it was Christian who introduced me into it. He sold me into this idea that the horizontal flow in foliations by hyperbolic surfaces was fascinating. When I was his PhD student, and he was my advisor together with Javier Gomez Mons. And when I started my PhD, I was well aware of the importance of the geodesic flow. And it was them who convinced me that the horizontal flow was wonderful. And it's an idea that stuck because I'm still doing this. So that's why I chose to speak about this subject, which is my oldest mathematical interest. So today I'm speaking about joint work with these people, Fernando Alcalde from Universidad de Santiago de Compostela, Françoise Dalbeau from Rennes 1, and Alberto Berkowski from UNAM. So since we're such an international team, we're thankful to the Institut Henri Poincaré, which made this collaboration possible through the program Research in Paris, which, by the way, was a wonderful city to be in. So what I'm speaking about is the following. So brief introduction. If you have a compact hyperbolic surface, such as the one in the picture, I'll be calling T1 of S its unit tangent bundle. And the geodesic flow on the surface, the phase space of which is, of course, T1 of S, is an Enosa flow. And its stable manifolds can be parameterized as the orbits of another flow, which is a horizontal flow. So here I've drawn a white geodesic orbit and an orange horizontal orbit. There's another viewpoint to study the geodesic and the horizontal flow on compact surfaces. So since the group of isometries which preserve orientation on the hyperbolic plane is the Lie group PSL2R, the unit tangent bundle to a surface can be seen as a quotient, as a compact quotient of PSL2R. And these flows, the geodesic and horizontal flows, can be seen as actions of one parameter subgroups of PSL2R. So there's a completely algebraic, let's say, viewpoint for this subject, and everything can be stated in the language of Lie group theory. So two classical theorems in this subject are Hedlund's theorem, which says that the horizontal flow is minimal in the unit tangent bundle of S, and Furstenberg's theory, which says that the horizontal flow is uniquely ergodic in T1 of S. So this is very much unlike what happens to the geodesic flow, which has many minimal sets, many different orbit closures, and of course, many ergodic measures. So in a sense, the horizontal flow is very well behaved. And in his 1973 paper, Furstenberg speaks about the horocycle flow being strictly ergodic, by which he means it's uniquely ergodic with respect to a measure of full support, which is, of course, in this case, the luvial measure. But this is a terminology that will come in handy. So what's our setting? In our setting, M will be a compact manifold, and it will carry a foliation by surfaces, that is by two-dimensional manifolds. So as you know, surfaces, according to how they are uniformized, can be the sphere or parabolic surfaces or hyperbolic surfaces. So most surfaces are hyperbolic surfaces. So, arguably, most foliations are foliations by hyperbolic surfaces in a sense which is topological. So there's a mild topological assumption that guarantees that each leaf has a metric, a Riemannian metric of constant curvature -1. And this is a theorem by Alberto Candel. And these metrics on leaves vary continuously in the transverse direction to the foliation, continuously in the smooth topology. So the unit tangent bundle to a foliation is simply you have the manifold M and the foliation F, and now if you're in a point, you take the unit tangent space to the leaf at each point. So this will give a manifold M hat that has one additional dimension, which will be a circle bundle over M, and that will carry a foliation of dimension 3, the leaves of which are the unit tangent bundles of the leaves of F. And this manifold M hat is the phase space of what we call the foliated geodesic and horocycle flows, which we will also call GT and HT. So what are these flows? A point in M hat is a unit vector tangent to a leaf. So this will be the initial condition of a unique geodesic on the leaf, which by Candel's theorem is a hyperbolic surface. And this is the, following this geodesic will give the geodesic flow. And the same is true for the horocycle flow. So it's important to picture the leaves of the foliations as being non-compact. So typically when you have the foliation MF, a leaf is immersed in the manifold M in some complicated way. It's usually a non-compact surface which is immersed in some complicated way in the ambient manifold M. And a geodesic on the leaf will travel on the leaf in some way which might not be completely trivial. So, for instance, if a leaf is simply connected, it will be a hyperbolic plane. So the geodesic flow on this leaf and the horocycle flow on this leaf are very simple if you think only in terms of the leaf. But the complicated way in which this leaf is immersed in the compact manifold M will give or the complicated way in which the unit tangent bundle to this leaf is immersed in the compact manifold M hat will give the geodesic and Horo cycle orbits some topological complexity that comes from the dynamics of the foliation. In fact, when we study foliation dynamics, it's quite a natural idea to follow the geodesic flow, because usually when we study foliation dynamics, we want to know where the leaves are accumulating at infinity, what the limit sets of the leaves are. And the natural way to get to this place is following geodesics along the leaves. So there's an alternative approach, which was introduced by Lucy Garnett, that has become more mainstream, which is following the Brownian motion on the leaves, so the Brownian paths, and see where they lead. And in fact, for foliations by hyperbolic surfaces, these two approaches are more or less the same. So the two questions we will be addressing are the following. When is the foliated Horo cycle flow a minimal flow on the manifold M hat? So this would be a foliated version of Hedlund's question or theorem. And of course, since the leaves of the foliation T1 of F are invariant under the flow, a necessary condition for this to happen is that the foliation itself be minimal, so that all leaves are dense. And the second question is, when is the foliated Horo cycle flow uniquely ergodic on M hat? So this would be a foliated analog of Furstenberg's theorem. So the first question, the question of minimality, has been addressed in several papers. So this is research that has been going on for a while. There are partial results. It is not true in general that the Horo cycle flow is minimal. For a minimal foliation by hyperbolic surfaces and a compact manifold. But well, there are partial results. But today I'll be speaking about unique ergodicity. So what do we know about unique ergodicity of the foliated Horo cycle flow? So there are basically two results as far as I know. So since there is this algebraic interpretation of the Horo cycle flow on surfaces, in fact, this flow comes from the action of a unipotent subgroups of PSL2R. Even in the case of foliations, you can reframe the problem in this setting. So Ratner theory will tell you everything you want to know if your space is a homogeneous space. So if your manifold M hat is PSL2R times some Lie group G divided by some co-compact lattice, you can apply Ratner's theorem here. So I remind you that the reason PSL2R is here is that PSL2R is the unit tangent bundle to the hyperbolic plane. So you can also read this as T1 of H, so unit tangent bundle to the hyperbolic plane, times G. The foliation here is the horizontal foliation, the foliation whose leaves are T1 of H times an element in G. And when you quotient this, you get a foliation in the quotient, which is the unit tangent bundle to a foliation by hyperbolic surfaces. So in this setting, you can apply Ratner's theorem to know what all ergodic measures invariant under the Horocycle flow look like. And what is key in this setting to establish unique ergodicity is the fact that Horocycle orbits are very well behaved. They don't diverge exponentially. So one thing which is key to Ratner's theorem is that if you take two initial conditions, which are very close, the first direction along which you'll see them diverge is the direction of the flow, then the direction of the geodesic flow, and then the other directions. And divergence of orbits is polynomial with time. So this is a flow which is really, really well behaved. And this is key to proof of Ratner's theorem. And the other setting in which something is known is quite different. It is a setting of foliated manifolds arising from the classical suspension construction with transverse projective structure. So what is this? You take a lattice in PSL2R, not necessarily co-compact, and you take a linear representation of this lattice into a finite dimensional real or complex vector space. So you consider the following manifold M hat, SL2R times the projectivization of the space V, where you quotient it by the diagonal action of gamma. Gamma is acting here by translations on the first factor and through the representation rho on the second one. So this will give you the unit tangent bundle to a foliation by hyperbolic surfaces, which has transverse projective structure. And under a generic assumption for the representation, this flow is uniquely ergodic. So this is a result by Christian and Javier Gomez-Mont for the case of fiber CP1 and CP2, and in general is due to Christian, Eskin, and Wilkinson. So this is a very different situation for the previous one because this generic assumption on the representation rho is an assumption on the Lyapunov exponents for the geodesic flow in the direction which is transverse to the foliation. And these exponents don't have to be zero. So in this case, you have exponential divergence or contraction of the distance between leaves. So the horocycle flow in this case has a very different behavior because the transverse dynamics of the foliation is it introduces some non-uniform hyperbolicity for everything which is happening on the leaves, or this might happen. So this is very, very different from Ratner's setting. So what is it that we do? We study Riemannian foliations. So a Riemannian foliation is something which is in a sense closer to the algebraic example. In the algebraic example, the transverse structure was modeled on a Lie group. And here the transverse structure is a structure of a Riemannian manifold where a metric is preserved. So that's not the definition, but sort of. This will be precise later. So there's a metric, a precise definition would be there's a metric for which the local distance between leaves is preserved. So the holonomy preserves distance. So this is closer to the algebraic setting, but it's not inside but it's by no means inside the algebraic setting. And these foliations are not that trivial. So in general, they have non-trivial holonomy. They may have leaves which have different topologies and so on. And another thing we have to deal with is even if there's a Riemannian metric for which the local distance between leaves remains constant, this is not the same metric for which leaves are hyperbolic surfaces. So we have two metrics here, the one that exhibits the Riemannian behavior of the transversal, and Candel's metric, which gives the hyperbolic structure to leaves, which is still only continuous. And in this setting, we prove that if you have a minimal Riemannian foliation by hyperbolic surfaces, the whole cycle flow on its unit tangent bundle is uniquely ergodic with respect to a measure of full support. I don't know if there are any questions. Please feel free to interrupt because I'm feeling very lonely here.
Well, if you have this is Steve, if you have a minimal Riemannian foliation, then Molino's theory gives you that it's a representation on a Lie group, the transverse structure group. So that looks pretty algebraic, though.
Well, we couldn't get the unique ergodicity from this remark, so we couldn't push Ratner's theorem into this setting. I mean, we did know that, we were aware of that. So
okay, but it doesn't help to know that you've got this the monodromy representation on the transverse structure group.
no, I mean, maybe you can do something with this, but we were not able to frame a general Riemannian foliation exactly in the case of homogeneous space, because so this result is simpler for Geely foliations, slightly, yes, but we weren't able to technically push this into Ratner's theory completely, no.
Okay, thanks.
So this is our results, and it has a corollary had been conjectured by Matsumoto, which is that if you have a minimal Riemannian foliation by hyperbolic surfaces, the whole cycle flow on its unit tangent bundle is minimal. So this had been proved by Matsumoto with the additional condition that there's a leaf which is not simply connected. And another remark about this result is that we have this issue with the regularity of the metric. So the geodesic flow is not partially hyperbolic dynamics with zero transverse Lyapunov exponents, because the hyperbolic metrics on leaves vary continuously in the smooth topology. So the geodesic flow, which depends on derivatives of the metric, is continuous, but we cannot guarantee that it's more than that. For instance, it's not C2 in general. Well, we don't know if it is C2 in general. We don't have any counterexample, but the smoothness of the metric is so far C0. And it's an open problem whether this metric is, for instance, smooth. So if you want to use Pessin theory in any way, you have to construct Pessin foliations by hand. So I want to step back a second and speak about why this problem of the unique ergodicity of the horizontal flow is not that simple. So what can go wrong in a more general setting? So the first thing that can go wrong is that the horizontal flow may have a lot of minimal sets. So unlike in the case of surfaces, orbit closures may be of different types. And an example of this is the following. If you take the cat map, that is a toral automorphism coming from the matrix 2111, the suspension of the cat maps gives you a 3-manifold M, which is a Sol manifold, that fibers over S1 with fiber T2, and a flow, which is the suspension of the map, which is an Anosa flow. So the foliation which we consider is the center stable foliation of this flow. And there's a natural metric for which the leaves are hyperbolic metrics, are hyperbolic surfaces, and the flow lines become geodesics. So this is what a leaf looks like. A center stable leaf will always be a plane or a cylinder. I've drawn a plane here, and the flow lines are the white lines, and they're parallel geodesics. And the stable manifolds are the stable manifolds of the points in the torus, in the toral fiber, for the dynamics F. So they're contained in a toral fiber. So the geodesic and the horocycle flows are flows not in this space, but in a 4-manifold, which is the unit tangent bundle to this foliation. But actually, if you take the vector field, which is tangent to the flow, this gives you a section of the unit tangent bundle. And inside the manifolds, which I have called M hat, you'll have an exact copy of the manifold M, which will be invariant under the geodesic and the horocycle flow and so on. So you can think inside this invariant set that the geodesics and the horocycle flow are the ones that have these flow lines, which I've depicted here in white and green. And the flow lines in M become geodesic orbits in this invariant set. The stable manifolds, which are green, become horocycle orbits in this invariant set. So there are horocycle orbits that have a torus like closure. So there's a 1-parameter family of the orbit closures, which give, of course, infinitely many ergodic measures for the foliated horocycle flow. In this example, the joint action of the geodesic and horocycle flow is known to be uniquely ergodic. So these are many measures which are ergodic for the horocycle flow and which are not invariant for the geodesic flow. And the next example is the following. Even if you have a minimal horocycle flow, for the foliated horocycle flow, minimality does not imply unique ergodicity. I mean, it's like life itself. And you can construct an example starting from a dynamics, which is minimal but not uniquely ergodic. So this should say F from T2 to T2, the two torus. A dynamics which is minimal but not uniquely ergodic. There is such an example due to Fustenberg, which is very nice. And I'll go quickly through this because I'm a little bit late, but from two different invariant measures for this dynamics, you can construct a foliation by hyperbolic surfaces for which the foliated Hall cycle flow is known to be minimal, but that has two different invariant measures, each coming in a natural way from an invariant measure for the map F. So here in this construction, F will be the transverse dynamic to the foliation. It's again a suspension. And each transverse invariant measure will give an invariant measure for the core cycle flow in a very natural way. So even in the case where you have transverse invariant measures for the foliation, which is very non-generic, you might have a Hall cycle flow which is uniquely ergodic, which is not uniquely ergodic, sorry. So what's special about Riemannian foliations? Well, as I said, one way to define them is saying that there's some metric for which local distance between leaves is constant. Another way to say this is that for some metric, if a geodesic is orthogonal to F, at one point it will remain orthogonal to F. And this is not the same metric for which the leaves are hyperbolic. So if you want a metric that exhibits this Riemannian transverse structure and which also assigns curvature -1 to the leaves, you can have this, but only for a metric which is continuous, and metrics and leaves vary continuously in the smooth topology. And there's a transverse invariant volume coming from the Riemannian transverse structure. And the foliated geodesic and Hall cycle flows are continuous flows. So the key to prove our theorem was finding the correct proof of the unique ergodicity on a compact surface. So Yves Coudin has a proof of the unique ergodicity of the Hall cycle flow in a compact surface, where he does the following. If you extract what the proof says, you get the following theorem. If X is a compact metric space, which has two continuous flows, G and H, which satisfies a commutation relationship of the geodesic and Hall cycle flow. So namely the Hall cycle orbits are contracted exponentially along the geodesic orbits. The flow H is topologically transitive, and you have a Borel probability measure which is invariant under both flows. And you add a semi-local condition involving the long-term control of the geodesic orbits, of the GT orbits. So this condition essentially says that you have a weakly stable foliation for which the measure mu is absolutely continuous. So I'm not saying the definition of these terms, but you have this local structure, then all this implies a unique ergodicity of the Hall cycle flow. So the main point here is that he manages to state all these conditions in a way which is suitable to deal with continuous flows, flows which have very little regularity. So what do we do? For us, in our setting and the Riemannian foliations, the measure is the transverse volume times the alluvial measure on the leaves. So this is what our measure looks like at a local level. So what we had to prove is the transitivity of the foliated four-cycle flow and that there is this local structure. So I won't be commenting on one. So transitivity of the four-cycle flow, I mean, it is certainly a necessary condition, but I won't be commenting on it. I'll be commenting on how we did the second part. So we started with the manifold M hat with the foliation T1 of F. And if you take a point V in this space and the local transversal, so a small transverse disk to V, you can construct a covering tube. This is something which is of the form T1 of H times sigma, which is surjective. It's a local diffeos. It's a local foliated diffeos, which means that T1 of H, each T1 of H factor goes onto a leaf of T1 of F, and along each leaf, this is a uniformization of the leaf. And then there's some additional condition of the transverse structure. So there are two ways I know of doing this. This can be done in general for foliations by hyperbolic surfaces. And this can also be done in general for Riemannian foliations, regardless of the leaf structure, which is what we did. So this is the covering tube, and the hyperbolic metrics vary continuously here. And this is, I've drawn in red the transverse section sigma, and I have my point V, which is an initial condition for a foliated geodesic. So the problem here is that metrics vary continuously. So all force bears these things. This should be a verb to straighten the metrics. So by this I mean you solve the Beltrami equation on these leaves to send the hyperbolic metric to a standard metric, which you choose, and you use a continuous dependence of the solution to the Beltrami equation with respect to the initial condition, and you get a thing which has where now all the hyperbolic metrics are the same. So this is a continuous change of coordinates, and the transversal sigma is something which is not as cute as before, but never mind. So now that all the metrics are the same, if I draw this blue transversal, all blue geodesics, so geodesics for all the blue initial conditions, stay at a bounded distance from the green one forever, because this is where the Riemannian conditions comes in. Because since the distance, local distance between leaves is preserved, any geodesic with the blue initial condition will follow closely the geodesic with the initial condition V. So what would be a weakly stable manifold for V? Well, it's something which will be like blue transversal time whatever was the center stable manifold on the leaf, which is two-dimensional, of course. So then you take this back with the continuous change of coordinates, and you have some sets which is I mean, the picture on the left is homomorphic to the picture on the right. So you will get some weakly stable manifold on the left-hand side of the picture. And you will have a weakly stable foliation, and you have to disintegrate the measure mu and see that it is absolutely continuous with respect to this foliation. But this is the idea of the proof. So the only thing that I have to say is happy birthday, Christian. Thank you very much.
Good. Any questions?
See, yes, maybe. Can you show again the last mathematical slide
Oh, it's so hard. Wait a minute. Yes, I can.
with the center stable manifolds? Well, no, so okay. Anyway, my question is the following: you have this foliation, and so the geodesic flow inside is some kind of hyperbolic, on transverse is Riemannian.
Yes.
So can we have some kind of shadowing lemma which give you this center stable manifold with no alpha burst? Because the geodesic in the next look like pseudo orbits for the flow. So we could make, I think could make it as a kind of shadowing.
Maybe, yes. You have to control what happens in the whole future.
Yeah.
So you have to have a way to really pick up the one initial condition in the transverse, in the nearby leaf that will shadow an orbit forever. And then see what this set looks like. So yes, I guess you could do could do another argument.
Maybe
yes.
you have better regularity by your way.
So L4 is like overkill so many problems that it was just easy to use.
No, one thing that I don't think there's uniqueness on the limit Riemannian metric. So it's conceivable that as you move transversely, the uniformation would rotate through Teichmüller space, through the space of negative curvature metrics. And that would force the geodesics to spread. As you move transversely, the horizontal flow would rotate, and that would break shadowing. You need some sort of projective statement that the metric on leaves comes from a base up to the total space. And then you have exactly your shadowing. But otherwise, it's not clear whether or not you could get a loop in the Teichmüller theory. Because you've got this transverse choice at every leaf. I'm
but
not sure
at the end,
works.
there is shadowing. The result proves that there is shadowing.
Yes, but this rotation is the funny thing. So we weren't able to do another argument. An argument was purely coming from hyperbolic dynamics that picked the exact point which would shadow it. I don't know. It was so first we did something. We used the slice theorem in the space of diffuse and I don't know what. So we had a previous argument before noticing that L4 was simpler, but it was not the kind of thing you're thinking about. But maybe that's just us. I mean.
Can I ask a question? Can you hear me?
Yes, perfectly, yes.
So you're working on this codimension 1 setting, right? Could you comment which parts essentially use codimension 1?
No, this is not codimension 1. So
I mean, I think you started with 3 manifold. What if you go to higher dimensional manifold, foliated by
no, this is for
everything?
Riemannian foliations of arbitrary codimension.
Arbitrary codimension.
It's
Okay.
always
Mhm.
the three-dimensional thing is the leaves. So the leaves are surfaces, so the unit tangent bundle to leaves have dimension 3, but it's arbitrary codimension.
Okay, thank you.
Maybe I have another question.
Yes.
Okay.
You give an example where the closure of the Rowe cycle was submanifold, that is tori. Is it is that some chance to have some generalization of that? That is, if it is not minimal, then the closure of
We know very few things when the Rowe cycle flow is not minimal, but we have examples where pretty ugly closures arrive. So, but yeah.
ugly closure.
No,
ugly?
I mean you can make examples in lamination setting, and you can do skew products with funny things, but we don't have examples where you have radically different orbit closures inside a minimal set for the geodesic and Rowe cycle flow. So we understand very little what orbit closures look like. We do have several sufficient conditions for the Rowe cycle flow to be minimal, but when it's not minimal, we have a very poor understanding of the dynamics. So have I answered?
More questions? Oh, if more question. I sometimes I feel a little strange that Christian has been 60 years old.
For me too.
But on the other hand, I think he has been a good friend of us for quite some years. And I just want to mention one thing, that Christian has several Chinese students. I think at least 4. I can name Ming Li. He was probably the first one, and then Da Wei, and then Yi Shi, and then Jinhua. Jinhua is the last. And also there's a Chinese postdoc there. I can't. It's like Yu Bing or not, and the name. So there are quite some Chinese still young fellows. They have been working with Christian these years. So that and also Christian has visited us several times, and he gave us lectures. We were still have very good memory. So yeah, it has been it happened a lot of things. So it's my anyway. I just say once again, happy birthday, and I just want I'm thinking about 20 years later when Jaco will be 100, and last year Christian will be 80. We will see what we can say, what we will say at that And happy birthday.
Yes.
Okay, maybe Lorenzo, I get back to you.
No, but then I think that I stopped the recording.